So, good afternoon, everybody. Dirk, are we online? Okay. And welcome to the LISA end of mission event. So I went for lunch today with people who know more about the mission than myself, with Ian Harrison, the spacecraft operations manager, with our good friend and partner from the science directorate, Martin Kessler. Glad to have you here. Our prime #1 customer in ESOC, and with Juan Miro. Now, about LISA, we will hear a lot. What do we do at ESOC? Since 15 years, we are operating space missions, some of them more challenging, others less challenging. And with LISA, every mission is special. LISA was special in a way that it's a mission to Lagrange point #1 at a distance of 1.5 million kilometers, and to bring a spacecraft from a launch on a Vega rocket, the smallest of the European launcher family, inserted in a 200 by 1,500 kilometer orbit, to bring it from there, from 200 kilometers in extreme case, out to 1.5 million kilometers with no gas station along the way. And this is a challenge in itself. And this is what I always say, ESOC is more than the mission operations, more than the control room that everybody knows. Before a mission goes to the launch pad, our flight dynamics people have designed a trajectory to get the spacecraft where we want it to have. And once again, we have all reasons, I at least have all reason to be proud on the ESOC team. And I'm sure the scientists are nodding. So I trust that good science came out of this as well. So we're having the honor at ESOC today to celebrate end of mission of LISA. When you do an end of mission, either something goes wrong, it's the end of mission immediately. When you run out of budget, there's a valid reason, and when you have accomplished the mission has done what it's supposed to do, and so two of these criteria, I guess, are true for LISA Pathfinder. From what I understood, LISA has overperformed, and so it deserves a rest. And we can focus then to go for the full Monty in somewhere in the 2030s is what I understand. So the PIs tell me ready to go, and in a humble way they say, well, not overstressed or overperformed, but from what other people told me, you can be quite pleased with what came out of it. So I guess somebody, PIs, this evening by 8 will push the button and deactivate the spacecraft, and then the spacecraft will orbit around the Sun, 200 within Earth's orbit, 2 million kilometers away from Earth, so in a safe distance, and it will have sunshine forever in the future. So at least for many, many, many years. So from a technical point of view, I understand this was proof of concept. PIs feel comfortable that we can go for the full Monty in 2034. I myself used to work in astronomy back when I was still working, but still about gravitational waves, I do not understand too much. All I know is what I learned over lunch, thanks to Ian and Martin. So I understand ripples in space is what gravitational waves are, most likely caused by collision of enormous masses like massive black holes going through matter, antimatter galaxies, and so on. Seems at least makes sense to me. I said ESOC celebrates its 50th anniversary this year, and over these 50 years, I think we have seen an evolution of, if not a revolution of astronomy. So during this time, we have seen the Hubble mission revolutionizing our understanding of the universe. We have seen, we have been on a comet with our Rosetta mission. We are still operating the Gaia mission, the Billion Star mission, which will be will create the reference catalog for generations of astronomical missions to come. So I think this is the time to congratulate the scientists, to praise team effort, two PIs, Carsten Dansmann and Stefano. So, yes. So thanks a lot for creating the idea. All the teams, to thank our good customers from the Science Directorate. Science Directorate today being represented by Martin Kessler, to express pride on our own people. And as I say, let's not fall in a collective depression. Let's celebrate success. Thank you very much.
With a bit of luck.
With a bit of luck on Windows.
Shall I press the button already?
No, it's pressed.
Okay, so thanks to Rolf for his introductory speech, and I would like to welcome you all. It's a little bit of a sad day because we're terminating a very nice mission. But as it was said before, we have a very good reason for terminating it, which is we have achieved actually more than we hoped for. And I think we will hear about this later. We have pulled together a little program which will lead you into all the depths of gravity waves and what it is all about, what we have achieved with the mission with our gravitational reference sensor, also called the LISA test package. We have also a short presentation about the DRS system, the disturbance reduction system, which was contributed by NASA from Phil Barella. And at the end, I think, the outlook into the future by Carsten. So you won't get bored, except maybe for the first 15 minutes, where I'm afraid I will speak. And Ian, we will talk to you a little bit about the operational life of this mission. Okay. Should work. Okay. So it's going to be an overview from LEOP until today. So effectively, a mission overview, for those of you who don't know, what Rolf said actually is pictured here in this diagram, giving a quick mission overview. We started with this mission on a very low Earth orbit, and then ended up in an orbit, operational orbit around Lagrange 1. And I can tell you on the 2nd of December, I think, which was the first launch attempt, didn't quite make it. There was a problem with Vega. We had to reschedule the day after. We were already inquiring about the possibilities of what would happen if the AWIM wouldn't fire all the way through, and whether we could recover the mission. But all of these scenarios didn't come true in the end. So it's a nice end of the story. But if we say we, at ESOC, well, normally when we present, we say we do LEOs, we do highly eccentric orbits, we do Lagrange missions, though except for interplanetary, which you get now in a way with LISA Pathfinder. At the end of the mission, we've done it all with one mission, which is LISA Pathfinder. We started up in a low Earth orbit, 200 times 1,500 kilometers, and all of this in X-band, which normally these missions at these low Earth orbits don't use. So this is just to recall the LISA technology package. You will see it in here. These two beautiful little cubes, very finely manufactured, in order to avoid any disturbances, and the laser system, metrology system in between to measure the distance very precisely. And this is the core of the mission, so to speak. That, by the way, is the science module on top of the propulsion module, which we used to get us to L1. And a short summary of the LEOP itself. We were launched, obviously, on the 3rd of December from Kourou. We had the countdown, launch and separation, the biprop system priming on the first day of the LEOP, the attitude acquisition, all went very well. Star Trek switch on, system checkout, it was all fine. And then, actually, we had left ourselves the margin of 2 to 3 days in order to see, in case things were going wrong, we had a buffer. And actually, not much was going wrong, but we needed the buffer because we had some issues with the star tracker, not exactly pointing, and we'll come to that in a minute, not exactly providing the outputs all the time that we expected. And there were some other challenges, and all of it took us a bit of time. And I think these 2 days really made a difference. Thereafter, of course, the orbit raising with 6 apogee raising burns in order to get out and a touch-up burn in order to get ourselves on a transfer to L1. And we can say after these 10 days, we'd actually achieved what normally you get out of a rocket which is properly sized for a mission. Effectively, you were on an escape orbit to L1, or an orbit to L1, getting away from the Earth. And so it was 3 kilometers per second and around 1,260 kilograms of propellant and pressurant. Okay, after this transfer to L1 commissioning activity started, at the end, the separation of SCM and PRM, before we started actually working with the science module, and Ian will come to that. So here you see what I mentioned before was the pictures of the star tracker, and it's, yes, you can see a little bit of sky in the background, which is over here. Here you can see stars, but all of this is, of course, Mother Earth. And here actually is a picture where the star tracker was looking with the bore side onto Earth, and you can see that. So it's quite rather unusual pictures. It's not an Earth observation mission. This was the orbit raising sequence, the plan, and you can see all the delta V's we did, and all of them very carefully planned and timed by our flight dynamics colleagues, and it worked pretty much to plan, except the later burns, of course, got a bit delayed because the orbits were slightly different from what we assumed, and there you get a little timing delay, but otherwise it was all fine. And this, of course, before I hand over to Ian, is an important souvenir for all of us who have participated in the mission. This was taken before launch on the 30th of November. It was the pre-launch picture of the mission control team. So credits for having achieved this first phase of the mission, very important, but in the end, when you see the signs, of course, that's even more important, but it was important to get us there in the first place. So thank you very much to all these team members who contributed. Thank you.
Okay, I'll try and take over from what Andreas finished and continue the brief summary of LISA Pathfinder from then until we are now. So it's going to be a very condensed version, but it will just give you a bit of background so that when the scientists give the interesting stuff about all the sciencey stuff, you've got a bit of background to how to plug it in for LISA Pathfinder. So after the LEOP finished on about the 13th of December, the next day, 14th of December, we started the commissioning activities. From the 14th of December till Christmas, we basically commissioned the service module with the support of Industrial Prime from Airbus and Stevenage. And then on the 22nd of January, just after Christmas, we did the propulsion, when we were finished with the propulsion module, when we were basically in an orbit that would give us a free drift into L1, which could be corrected with the micropropulsion system. We did the separation of the propulsion system from the science module, and after that, we could then release the test masses. So this happened on the 22nd of January. As you see here, you can see the spin up, which happened in about, 10 seconds, 20 seconds. And then the spin down with the micropropulsion system, which took about 9 or 10 hours. In fact, the winner of the sweepstake, where's Dave? How long was it exactly, Dave? We had a small sweepstake here on the duration it would take for the D-spin, and Dave over there won the sweepstake. It took a lot longer than we thought. At the start, you see it decelerating very quickly, but this denutation phase took a lot longer than we thought, and hence it took us a lot longer to despin the whole spacecraft. Immediately after Christmas, we started the DRS commissioning. So I think this was the 2nd of January. I don't think we did anything on the 1st. We took Christmas and the 1st of January off, and then the 2nd of January, our JPL colleagues were over here in the PISA room, and we started the DRS commissioning activities. Following that, the first couple of weeks of DRS commissioning, shortly later we then released the test masses, and these were on the 15th and 16th, I say of January, it's actually the 15th and 16th of February, so I need to correct that. So here you can see quite clearly, this is the first one, where's the pointer? This is the test mass 2, which was actually quite problematic. After we released the test mass, it got stuck in the corner and required a few small nudges from a plunger. So this is a mechanical finger that normally contains the test mass. We needed a small nudge of the test mass to release it again before it could get controlled by the electrostatics. And this here is the test mass 1, which behaved itself very well, a lot better, but still you can see 1, 2, 3, 4 impacts where it bounced off the plunger or the wall before we had damped the velocity down sufficiently for the electrostatics to capture it. But still, after those 2 days, we'd got both test masses electrostatically controlled, so sensing and actuation by the electrostatics within the test mass enclosure. After we'd done the commissioning activities, which completed on about 29th of February, everything went to plan. We had problems during the commissioning, but they all were resolved within the time scale of the commissioning activity itself. And so even though the test mass release on the 15th and 16th were exactly at the times they were meant to be released, and we had the in-orbit commissioning review in the first week of March that year. But before that, the project manager had already given us the unofficial go-ahead to start with the routine operations phase. And basically, straight away out of the box, the LISA test package and the LISA Pathfinder itself worked better than anyone could expect, basically matching the specifications of the LISA mission itself, straight away out of the box. And then the scientists and the science working team and the science operations team started improving this performance, or measuring the performance and improving it over the next 4 months. After 4 months of operations of the ESA LISA test package under ESA control, we handed over the operations to the DRS phase. So we had 2 weeks of commissioning activities with the JPL team here on site from about the 26th of June to the 8th of July. And this is when we did the second phase of the NASA DRS commissioning, where we had closed loop control. The first phase was a checkout of the hardware, and this phase is where we actually handed over control of the whole LISA Pathfinder spacecraft for the DRS control. This all went very well. Shortly after we started the routine phase of the DRS, we had a small issue with the DRS cluster 2. One of the circuits failed and required a small update to the DRS flight software. So we temporarily handed back for LTP operations for a week or two while the DRS fixed this in the flight software, and then we will continue the DRS operations phase for another few months. And then we had another small problem with the DRS thruster 4 towards the end of their phase, and then again we worked this around and we ended up continuing with the DRS operations until early December. In this phase, we're using 4 of the coal gas thrusters in fixed thrust mode to provide a small force torque crutch for the DRS to act against, so they could conduct their science operations, DRS science mode. After this, we actually started requesting for the extension of LISA Pathfinder almost immediately after launch. So I think we're having discussions pretty much just at the end of the commissioning phase for the extending the mission, because the mission would normally end on the end of October. So straight away, by the summer of 2016, we had an agreement to extend by 6 months the LISA Pathfinder operations, and this was until the 30th of May 2017. And then we managed to stretch the budget envelope a little bit, so we actually ran science operations to the end of 30th of June 2017. Also in this phase, we ran a small experiment on the side on one of the star trackers, on the redundant star tracker, a small NEO experiment to try and use the redundant star trackers on board a spacecraft to detect near-Earth objects, in particular asteroids. I've got a couple little movies here, hopefully, oh dear, maybe they won't work. A couple little movies there for some of the results that came out of it. And this is in the first weekend of operations of the star tracker in the NEO mode. Hopefully it will start up. And this is the type of thing they were looking for, a blank screen. There's not a lot you can see, but right in the middle of the screen, if you look closely, you can see what looks like a little an object passing through the middle. And this is all they're looking for their star tracker operations. Each one of those frames is 1 hour of integrated time over the star tracker. They then merge them together, and they're looking for objects moving through their field of view. And this was in the first weekend. They found a couple of objects, and since then, I believe they found a lot more. Still waiting for a presentation for all the science data from them. But my understanding is they've found quite a few other asteroids, including known asteroid events. So I think for them, it was a big success, and we ran it for about 6 or 7 weeks on LISA Pathfinder. During the middle of this extension phase, on the 9th of April, we actually conducted a 1 meter per second delta V burn to basically dispose of the LISA Pathfinder spacecraft. So this then pushed the LISA Pathfinder the other side of L1 into a heliocentric orbit. And from then, we've not been able to recover the mission. At that point, LISA Pathfinder was always going to leave the L1 orbit and would go into a heliocentric orbit just inside that of the Earth. We had a few small issues with short-term replanning due to underperformance of coal gas, but all these were worked out. And the scientists quite liked from then onwards because we didn't need to do any station-keeping burns. We were leaving L1. We'd stay within the L1 zone for at least another 3 or 4 months to complete science operations, but no more science operations were needed. Let's go to full again. And this is a small chart from mission analysis colleagues. They've crunched the final orbit the LISA Pathfinder is in, and their estimates with using the latest orbit that we have from LISA Pathfinder, they say that the chance of return to the sort of Earth-Moon system, which means under their assumptions within 1 million kilometres of the Earth, are less than 0.2% over the next 100 years. This is what we're aiming to achieve. We're hoping to achieve sort of less than 1%, and currently we're at roughly less than 0.2%. We'll rerun these figures again when we get the final orbit next week or so, or sometime later this year. But at the moment, they're very happy with this disposal around the Sun. The final last 2 weeks have also been quite intense. We stopped the science operation phase on the 30th of June. And for the last 2 weeks, we've been running various hardware investigations coming in from various hardware providers, industrial prime, etc. So we've run a number of experiments on many of the subsystems on board both for the service module, the power thermal, the coal gas, and also on some of the payload aspects, the ISFE, the phase meter. We ran continuous discharge and a few other things which we hadn't managed to do during the normal mission phase. So we managed to try and pack in a lot of hardware runs in the last 2 weeks. Usually the ones that are slightly, a lot higher risk that we couldn't possibly do while we still had the science operations running. Some of these will feed straight forward into future missions like Euclid. We had the Euclid team here observing some of the coal gas checkout, and some would hopefully help the LISA mission, particularly those for the ISFE, new actuation algorithms, etc. Yesterday, we switched off the LISA test package around 1500 Zulu, and we grabbed the test masses around 1430 Zulu. We've passivated the A side with the corruption of the E2-prom decompression algorithm on board on both E2-prom images on the A side, and we completed the final dumps of the science data. We ran a small science mode over the weekend. We ramped up to science mode again and ran a smaller signal on the test mass 1 and 2 because there was a small solar activity event over the weekend. So hopefully that data will be down on the ground now. We had dumped through till 16 Zulu yesterday, or the end of the pass yesterday. So this thing can be looked at offline. So everything is completed on the spacecraft side. So today we're going to do the final side. We'll switch to the B side of the data handling, which we've never used before. So hopefully the processor module B powers up. If not, we'll have switched it off early. But hopefully it will power up at the start of this pass, and we'll then again corrupt the B side E2-prom with the decompression software, and then the final commanding will be sent by Stefano, which will be the final switch off, which is the activation of the corrupted software image and the switch off of the transmitters by both relay and LCL. So we have a double barrier against the transmitter coming on again. Anyway, that gives everyone a quick overview of LISA Pathfinder, where we've been launched until now. And now I think what most of you will come for, which is the really interesting stuff about the future and all the sciencey stuff that's been processed. So I'll pass over now to Paul, who'll give you a summary or an intro into LISA Pathfinder science. Now I'll run off. Cool. Oh, no.
Yeah, it's not much use, unfortunately. I'm afraid I'm going to take this off. It's easier to walk around with it. So thank you very much for being here. It's a kind of bittersweet day today because we're coming to the end of this one. You see we're all wearing black. It's a bit unfortunate we all have black T-shirts, but we're here to celebrate Pathfinder, not to mourn the end of the mission. So we've got a couple of talks. I'm going to give a kind of a general overview of LISA Pathfinder, and then hand over to Stefano, and he'll go through the details of the LTP part, and then Phil will talk about, wherever Phil is somewhere, over there. We'll talk about the DRS and then just about LISA. So let's kick off. So what is Pathfinder? Well, as we say, it's the first steps to observing gravitational waves from space. We'll come back to gravitational waves in a minute. As we heard, it was launched on the 3rd of December 2015 on a Vega. Our science operations ran from the 1st of March through to the 30th of June of this year, 1st of March 2016. And the takeaway message from everything today is the performance of this spacecraft and instrument has surpassed even our wildest dreams. You know, if you'd asked us on the 2nd of December, let's say 2015, what would we have achieved? We would never have guessed would have been as good as we are. It's just been an absolutely wonderful mission. So Pathfinder essentially is not a gravitational wave detector. So we take the millions of kilometer arms you would have for something like LISA, we shrink it down to 40 centimeters, put it inside the spacecraft, and that becomes LISA Pathfinder. So we can't measure gravitational waves, but what we do is we maintain all the instrument noise, everything which could perturb the gravitational wave measurement. That's all local to the spacecraft. So we maintain that, and we actually make it worse, because we've got the two test masses sharing the same arm in a spacecraft. So Pathfinder is actually harder to do than LISA. But gravitational waves. So what are gravitational waves? Actually, let me just plug this thing in, I can walk around a bit. So if you go way back to Newton, then we had this instantaneous action at a distance. So something happened in the universe and you knew about it, so time was not relative. And it doesn't work. Okay. It does work. But then Einstein came along, and as we know, Einstein said that nothing can travel faster than the speed of light. So if you're sitting here on Earth and something happens somewhere in the universe, there has to be something carrying that information, that gravitational information to you, and that's what we call gravitational waves. So gravitational waves, they're ripples in the curvature of space-time, as we heard earlier. They're produced by the motion of mass and energy. This is any mass, any energy, wave in your hands. That will create gravitational waves, any acceleration of mass and energy. And you see this, I was going to use that doesn't work. But you can see the waves emanating from the binary stars on the top right-hand corner. And they're creating these waves. And that's what we're trying to measure. We're trying to pick up the motion of the universe itself, which is vibrating. Now, mass and energy, if you look down at the bottom right, you can see this is our sort of understanding of the universe after Planck, where we have about 4% of the universe is the stuff we know about, the baryonic matter. About 0.4% of that is the stuff that shines. So we know about 0.4% of the universe is what we can see. About roughly a quarter of the universe, 23%, is dark matter. And about 3/4 of the universe is dark energy. So most of the universe is dark. And for people who don't know astronomers, when you don't understand it, you call it dark or black. So in this case, we're dark energy, dark matter. But we might actually be able to start, well, we know that dark matter interacts through gravity. And with gravitational waves, maybe we can start to probe the dark side of the universe. We can start to see, feel dark matter. So that's one of the reasons why we're really interested in doing gravitational waves. Now, gravitational waves travel through the universe almost unimpeded. They do get some slight lensing. But that's great, because it means that you can look to the far reaches of the universe. You can look right back to the Big Bang, in principle, with gravitational waves. So it's very nice as a tool to observe the distant universe. It's very bad in the sense that they're very hard to detect, because they don't interact. And so that's why in the universe, space is very stiff. It doesn't like to warp. But we have to build something which can measure this entity, space-time, which doesn't like to move. And that's the difficulty with gravitational waves. And these things are quadrupole in nature, so there's not like a dipole. If you put a little cork in the water, it bobs up and down. Here you've got to imagine that the wave is traveling along this kind of caterpillar-like thing. And if you look at it edge on, you can see it's stretching and squeezing, stretching and squeezing. So as the wave is coming towards me, I get slightly taller, slightly thinner, which is good. Next half cycle, I get slightly shorter, slightly fatter. That's not so good. But you can see how you measure gravitational waves. What you really want to do is you want to measure this axis with respect to that axis. Or as Steph will show, you can also do it with triangles. You can measure this line with respect to that line, and that will give you a good measurement of a gravitational wave. And that's why LISA happens to be a triangle. So gravitational waves carry entirely new information about the universe. Let's move things up here. So what? There's a nice little illustration to show you why do we want to measure gravitational waves. So here we have, looks like we're in a jungle somewhere, nice waterfalls. It's more of a jungle. There's some trees, there's some clouds. But so what? Now you turn on an extra dimension, and suddenly your jungle comes alive. You hear there's monkeys in there, there's birds, there's various things. You hear the waterfall before you even see it. Through the part of the universe, the part of the jungle is opaque. And suddenly this is no longer just a couple of trees and some clouds, it's a whole living ecosystem. And that's what gravitational waves is giving you. It's giving you that whole new dimension to the universe that part will never be able to see. So, again, if we'd done this presentation 2 years ago before launch, this chart wouldn't be here, because this was the first ever measurement of a gravitational wave. We call it GW 150914. So 2015, September the 14th, the first ever gravitational wave was observed by the LIGO detectors in the US. Now these detectors are big L-shaped interferometers. From the center to the end is about 4 kilometers, actually it is 4 kilometers. And when the gravitational wave passes, these arms change by a tiny fraction of a meter. Here we're talking about 10 to minus 18 meters, something on that level. So almost nothing, something around about the classical size of an electron. And this is a signal, you can see, well, again, can't point with that. Here you can see as the gravitational wave came, the signal got up, big signal, and then dies away. And that is, I'll show you in a second what that is. That's the two sources orbiting each other. And if you put that and play it through a loudspeaker, it sounds like this. It's transposed up so it's a bit easier to hear. And back to the original data. Again, transposed. And that was the first ever measurement of a gravitational wave. And what you're really seeing there, clear to see, but you're seeing there's 2 black holes. These 2 black holes are about 36 solar masses for the big one, 29 solar masses for the small one. They're located about 1.3 billion light years from Earth. And they've been orbiting each other for a very long time. And as they get closer together, if you look at the top right, you'll start to see the simulation of the waves passing. And as the black holes get closer together, they get a bit faster, the waves pick up, you see the Earth starts to wobble, and eventually they form one object, and that's the signal. So that's what we saw in the last chart, where this signal starts to get faster and faster and bigger as the 2 black holes are merging. And this put out a phenomenal amount of energy. This is one object, this one source of gravitational waves emitted more energy than the entire universe put together, entire electromagnetic universe, one single source. And this is roughly a stellar mass black hole, something in the order of tens of solar masses. There are many other, well, I'll come back to that in a second, but there are many other types of black holes, supermassive black holes, and that's what we're looking for in LISA. But the question is, so we're gravitational wave scientists, so to us, gravitational wave, the first detection of gravitational waves is very, very important. It's the breakthrough of the decade, if not the century. But really, is it an important discovery? Well, PhysRev Letters is one of the top journals in physics. The paper was published in it. If you're a scientist, get your paper published. That's good. We actually even got onto the front cover of PhysRev Letters. That's very good. That shows that it really was the best paper of that month. If you look at the date, you may not see it there, but that's 12th of February 2016, the paper was published. Not only LIGO got on the front cover of PhysRev Letters, but so did Pathfinder. A few months later, we also made a front cover. So again, we were delighted. Big review, big paper, we were on the front cover. It's important. But only scientists read these journals, no one else. So was it important? Yes. Made the front cover of New York Times, and Carsten can probably tell a number, but 200 and something front pages? 671 front pages around the world carried the story of gravitational waves. But newspapers are old hat. No one reads newspapers, do social media. Well, along came Barack Obama. Einstein was right. Congrats to NSF and LIGO on detecting gravitational waves, a huge breakthrough in how we understand the universe. Great. However, some people think fake news can't be right. So, how do you know you've made a massive discovery? Well, if anyone watches The Big Bang Theory, you know Sheldon, well, again, you can't see it, but he's wearing the gravitational wave. That means then you know you've really made it. And he's actually quite a big fan of us, because that's actually a picture, I think that's actually a LISA picture, where he's showing the 2 black holes merging. So, yes, it is a big discovery. But this is the spectrum. So, LIGO was looking for things roughly the size of the sun, so 1 to 100 times the mass of the sun, black holes. But you can look at objects throughout the universe, not only the small objects, but the supermassive objects. And if you look at this, the whole spectrum of gravitational waves. So if you go to a bit lower frequency, which means more massive objects, you have a space-based interferometers, why we're here today, to talk about LISA. And there we're looking at things like supermassive black holes, galaxies merging. We're looking at small black holes fall into big black holes. We're also seeing lots of objects in our own galaxy, compact binaries, so white dwarf interacting binaries. All of these things are emitting gravitational waves which we can measure. So one difference between LIGO and LISA is signal dominated. When it goes up there, it's going to be flooded by data. Whereas in LIGO, we're still waiting for signals to come. So it's getting not transient, but burst-like sources. We can then look at very low frequencies. We can use pulsars, so use the universe itself as a gravitational wave detector, and measure the timing of pulsars surrounding the Earth, and you can look for variations, modulations in the pulse arrival times, and you can use that to measure gravitational waves. Or you can look all the way back to the Big Bang, and you can use things like Planck to look at the polarization of the cosmic microwave background, and again infer the gravitational waves which have been imprinted onto the CMB. But we're here to talk about LISA. So this is LISA. It's 2.5 million kilometers between the satellites. This is not to scale. And they tumble, they just fall around the Earth. So if you look inside, or you look at LISA itself, what is it? So we have 3 spacecraft, separated by millions of kilometers, and the only link between the spacecraft is laser light. And there's not a lot of laser light. We're shining about 2 watts of light out of the, oops, there's some writing up there. There's 2 watts coming out of the spacecraft, and we detect a few hundred picowatts, so almost nothing at the far end. That's enough for us to make this measurement. And when a gravitational wave passes by, LISA is sensitive to any changes in the length of the millions of kilometer arms to about the 10th the size of an atom. So phenomenal, tiny, tiny amount over millions of kilometers. And if you want to scale that up to say, what does that mean? Because it's kind of hard to tell these numbers. If you were to scale LISA to be the distance between the sun and the next star, it would change that distance by about a millimeter. So you think about a millimeter is something you can comprehend. The next distance to the next star you can't, but you just know it's far away. That's the sort of precision we have with an instrument like LISA or LIGO. Now, very often people ask, especially around about now, says, now you have LISA Pathfinder, what are you going to do next? How do you get to LISA? And we always say, no, that's not right, because LISA came first, and then LISA Pathfinder came after it. So this is LISA, very quick description. It's 3 spacecraft, separated millions of kilometers. And scientifically, the role of each spacecraft is to protect a fiducial mass inside. In our case, a fiducial mass is a gold platinum cube, 2 kilograms of gold platinum, 46 millimeters on the side. And the spacecraft basically flies around the cube. So I have to take my mic away here, but if this is the cube, the spacecraft around it, as the cube moves, the spacecraft follows. So scientifically, that's its role. Of course, it also does avionics, power, all the rest of it, but not from a science side. If we look inside one of these guys, what we have is a telescope to get the light between the spacecraft, an optical bench, and this little orange cylinder which houses the gold platinum cube. And what we can do is we can measure the position of the little cube. We can measure capacitive sensing for 6 degrees of freedom, so we know exactly where it's moving, position and attitude. And we also have a high-resolution laser interferometer measuring the distance, longitudinal distance, and the attitude around the laser beam. We then take those signals, we feed it back into the control system, which we call DFACS, drag-free and attitude control system, and we feed that back to the spacecraft, and we make the spacecraft follow. And that's a rough idea. We then build up the arm of LISA. We don't do it directly. We measure, here it says PM, which is proof mass or test mass, to the optical bench, which is the spacecraft. We then measure spacecraft to the other spacecraft, millions of kilometers away, and then we measure spacecraft to optical bench. And by summing the 3 measurements, you get the distance between the 2 cubes. You do the same on the other arm, you do a bit of magic, and you end up coming out with your gravitational wave signal. So what is LISA Pathfinder? How does it relate to this? Well, we have 2 test masses in our little, now they're no longer orange, but they're see-through, but in the vacuum enclosures. We have a laser interferometer measuring position of a test mass with respect to the spacecraft, the same as the LISA local measurement, and also test mass to test mass, which is not the same as a LISA test mass to test mass. We have the capacitive readout in all axes, exactly the same as LISA. We have the drag-free attitude control system, almost identical to LISA, and we have micro-Newton thrusters forming the control loop, the actuators. You put all that together and you see it looks very much like LISA. Now the reason we have 2 cubes on here is essentially one is a witness to the first one. Now if you have a very good clock, how do you know it's a good clock? Well, you compare it to another one, and that's what we're doing here. If we only had one little cube, we tried to measure it, the only thing we'll actually measure is the position of a spacecraft, because the cube is so much quieter than the spacecraft is. So now just to give a little bit of history. This is going back quite a few years, 1996. Anybody who's got very good eyesight might actually recognize some people here, but this is a list of the people who are still actually working on LISA and on LISA Pathfinder in this picture. But if you look very closely, you'll see some familiar faces. I'm the one at the back. Carsten Dansman down here, the PI of the mission, is sitting, I'll point him out, sitting in here in the spacecraft. Harry Ward is somewhere around. Over there. Yep, Harry's there. Dave Robertson is probably also somewhere around up at the back. And Oliver, who was sitting here a minute ago, has now left. So some of us have quite a history in this mission from 96 through here. And also people like Stefan were also around in those days, but had left, I think, by that point. So it's not in the picture, unfortunately. Yeah. However, that was LISA. So that was the first LISA symposium, 1996 in Rutherford Labs. But LISA Pathfinder came into being in 2000. So we actually had ideas in the early days, 98 with the first sort of concept of it, but 2000 is when LISA Pathfinder entered the ESA system. And that happened to coincide with the third LISA symposium. And this is the recommendation from the SSAC that says, the SSAC unanimously endorses the executive proposal to use SMART 2 mission as currently scheduled as a timely opportunity to test the technologies which are crucial to LISA, blah, 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 blah. So the timely part. Well, it was timely. It was only 15 years later, and there we are at Kourou. Pathfinder is sitting behind us. It's sitting in the launch tower. And you can see there's some familiar faces again. Actually, in the first one, you can see the regular people. There's Harry Ward is here. He's over there, and myself. I'm in there somewhere. But this is all about the life of a PI. For the young people in the audience, do you really want to be a PI in a mission? Well, that's it. Well, forget the 15 years. That's what happens if you're the PI of a mission. You notice that Karsten's still smiling, so it must be good. So what is Pathfinder? So, as all missions in ESA, we have a split between spacecraft and payload. So the spacecraft is provided by ESA through the industrial prime contractor, which is Airbus, DS, and Stevenage. There's probably a bunch of the guys over there from Stevenage. And because of the traditional split, things like the thrusters and the control system are part of the spacecraft, whereas there's no real distinction in LISA Pathfinder or LISA between what is the control system, the thruster, and the payload. The whole thing acts as one unit and the whole one science instrument. We then have the payloads, so we have a LISA technology package, and that's provided by the member states in ESA, and then with the architect coming from Airbus DS in Friedrichshafen, from Rudiger, sitting here. And here we had the inertial sensors, so these little cubes. The interferometric system in between, and the whole diagnostic package, all these cabling running around here. We also have a disturbance reduction system, which Phil Barella was going to talk about later, and that's provided by NASA JPL. And this is running the processor, the control system, and the thrusters. So I say there's a traditional split on our side, but on the US side it's called a payload. And Phil tells a lot more about that. And this is where the parts came from. So you see we're all over Europe. We cover quite a few countries, 7 countries, and there's various aspects coming from there. And it's quite, it's interesting to note here, this is a very complex mission. So there's no distinction between a payload and a spacecraft. There's no camera number 1, camera number 2, diagnostic number 3. This is one instrument. This is one instrument, complex instrument, coming from these member states, all coming together and working on day one. As Ian said, very first day of operation, this thing worked straight out of the box. And we can't stress that enough. This has really been a wondrous mission, and to show the collaboration you can get in a complex entity like Pathfinder. So now a little bit of history. We've been around for many years. I say the first sort of idea of a demonstrator was called Elite. Anyone who's got sharp eyesight will notice that when this was first sent around and people looked at it, someone shouted out, "There's a spelling mistake in the front page." And of course, everyone laughs. Yeah, of course there is. Well, we've got the demonstration Staylight for LISA. If anyone doesn't see it, look at satellite and you'll see. And this is actually a picture of the front cover. There was a spelling mistake. But it goes to show that even with the spelling mistake in the front cover, we still got it there. That was 98. This was then refined and became SMART 2 around about year 2000. And you see there's, again, 2 little cubes sitting in these houses and the optical bench in between. And in those days, this was a part of a bigger entity called the Darwin Earsay LISA Pathfinder DRS. It was a kind of 3 entities in one mission. And the actual LISA Pathfinder part are these coloured boxes sitting over here. So it's a very small aspect of the satellite. Then we go for selection. I guess something more realistic, something that looks like something we can recognise today. 2 test masses, optical bench. We get adopted. It's something that looks even nicer. This time we have the Americans also had test mass and interferometer at that point. Unfortunately, that was descoped, and we're back to LISA Pathfinder. Then it's something which is very close to flying, and finally we get the flight unit. Then that gets integrated. I apologise for the shaky hands here, but whoever's taking the image just held a camera in their hand, and it's, with high zoom it doesn't work very well. But just to show that it was actually put inside the spacecraft, so we're not lying to you, we give you these wonderful results. And that was in IBG. So then just about 2 years ago just now, the thing was put in the Antonov, the whole spacecraft. It was shipped out to Kourou. When it arrived, it was rather wet. Luckily, the spacecraft survived. It was in that nice box. However, several computers died as people were carrying their laptops in their backpack, and the rain was so heavy it basically fried the computers. So that was a bit of a problem for the team over there. This terrified us. We see this picture, that the whole thing was shipped on its side. So why did it ship it vertical? But it's going to survive launch, so it can easily survive a flight on its side, and it did. It was then made vertical, final checks. The little spacemen come out and they put the fuel into the tanks. And then the fairing gets closed and it's all ready to go. And we can do a quick summary of that. Is it going to work? Yep. So the first thing we have to do is make sure it fits the payload adapter fitting. It then goes into the fairing. You'll see the people in the window getting a bit nervous. The reason they get nervous at this stage is they've worked on this for many years. Many people have worked on this for many, many years. As soon as the fairing closes, you never see it again. The next time the fairing opens is on orbit. So it's gone. It gets taken out to its transport module and then goes for a nice little trip through the French Guiana jungle. You don't want to have a clean room close to the launch site. If you do that and something goes wrong, then you lose your clean room as well as your launch site. So it's about a 10-kilometer drive. It took a bit of time, we get late at night, and then the terrifying part is you see the whole thing being lifted up in a crane. And that's a bit scary. Obviously, we've done it many times before, it's still a bit scary. It gets put down there, we'll forget a couple of days of hiccups when some bolts didn't work quite right. But it all closed up, and the next time it came out, it was ready to go. It was ready to launch. And then we can't do a talk
10,
about a mission without this part.
8, 7, 6,
So 3rd of December, 0404 UTC,
3,
off it went.
2, 1, top, allumage et décollage de
And it goes very
VV06.
fast, it's like the fireworks, a solid rocket booster. We had good weather for most of the time we flew, apart from that day. We had 11 seconds of light, and then that was it. Into the clouds, and we saw it for about a fraction of a second later, but not much more. But it was great, and as we heard in the last talk, we were put into low Earth orbit, 200 with 1,500 kilometers. And then we had to do the 6 apogee-raising maneuvers. I would stress it a bit more than Andreas did, even though Andreas is, it's his team. We had to do 4 maneuvers within, I think it was 40 hours. I mean, Ian or Andreas can keep me right here, but it was very short. And each one of these maneuvers, you have to know where's the spacecraft, what they have to do next, implement it, get the data. It was very intensive. But we got out there. It took about 50 days to get to L1. We separated from the prop module. I actually had that date wrong. I had 2nd of February. Ian had a bit earlier than that. And then our final orbit is about 500,000 by 800,000 kilometers. And at the moment, we're just coming round about where this stops. We've done about 3 orbits around L1 up until today. So what happened? We got there. So that's a very brief timeline to what happened. So we launched, we started commissioning. Now, we didn't have anything like an orbit insertion. So we go out there, we just separate, and we get what we get. So we didn't have to have the worry of, do we capture the orbit? For us, the main stressful part was we have to release these little test masses. So we release the launch locks. Well, that's fairly simple. But then we had to release the test mass to make it free floating. And that's the thing that Ian was showing. And we were quite relieved when this happened. And as you can see, this was the project manager who's thinking, good, I can go home now. So it was good. So then we entered science mode. Our first entry during commissioning, 22nd of February. We started science operations on the 1st of March. And by the end of the 1st of March, we'd met our requirements. So it was wonderful. We then ran through until June. We were handed over to DRS. DRS operated for about 3 months. We had actually handed back and forward over that period, it's a bit longer. And we started our extended mission in December of last year. And then the end of science operations, 30th of June. And then in about, I don't know what it is, 3 hours' time, we send the last telecommand. And that's end LISA Pathfinder. So we are a physics lab. We're not a standard astronomy experiment. So what does a physics lab actually mean? And it starts off with most days we get together and we work out what we want to do. So we get experiment planning. And that becomes a human readable input called the agenda file. It may not look human readable, but that really is a human readable input. And we hand that over to the STOC, in our case, Science Technology Operations Center. So normally the SOC or the STOC would be based in ESOC in Madrid. But for this mission, everyone was co-located at ESOC. So over here in the PISA room and over next to the dedicated control room of Pathfinder. And that was essential for the success of this mission, having everyone close together to discuss things, any issues, we could solve them very quickly, and it really worked. Then we gave it to the STOC. STOC are mostly engineers, so the guys are sitting here, so forgive me. But they don't trust us, so they simulate it. And that's not a bad thing, because many times there was mistakes. So that was good. They simulated, we iterated, we got it working. The STOC then send everything to the mock. we're surrounded by Mach here, but Mach don't trust anyone, so they simulate it. And when they're happy, then good, we can send it to the spacecraft. So everything's up to the spacecraft. It's back down again. We get it, and it runs overnight, or actually runs for roughly 3 days in the future. We're running 24-hour exercises. We get the data, the Mach convert it for us. It goes to the data analysis team. The data analysis team analyze the data and feed back the planning. So for the first 6 months of the mission, this was happening 7 days a week. We were continually getting data, replanning, sending to the spacecraft, and this was really intensive. And again, it got to stress, it would only have worked if we're here. It wouldn't have worked if we'd been remote in institutes or back in ESTEC. And we did lots of experiments. So this was for a nominal mission. This was roughly what we did. All these colors represent a different experiment. So Stefano's going to go through this. I'm not going to talk about this. I'm just going to mention one part, which maybe Stefano won't, is on their optical metrology system, how well we did there. So 2 things, one to do with Pathfinder. One is, how well can we measure the position of our test masses? And the second one is, how quiet are the test masses? So I'll talk about measuring, and Stefano will talk about the quietness. So this is the optical metrology system of the year 2000, when Pathfinder Smart 2 was first envisaged. And this is a bit unusual, because this is a fairly complicated system, and the actual flight system is much simpler. So in the one on the left, we have things like a reference cavity, we have Faraday isolators, polarizers, EOMs. The one on the right is just mirrors and beam splitters. So it's nice to see that things don't always get more complicated. Actually, sometimes get a bit simpler. And that's our OMS. And that's what it looks like in real life. We have a zero-door bench with little mirrors bonded onto the surface. This bonding is a hydroxy-catalysis bonding. And it forms things like a chemical bond. So it looks very fragile, but it's actually extremely strong. You can't get these mirrors off. And this is the University of Glasgow developed this system. And actually, if you look straight through here, you can actually see the test mass. That's about the only time you could ever see the test mass. That's you sitting at test mass number 2, looking at test mass number 1. And one of the things we're very worried about is taking a precision interferometer, putting it in space, and hoping that nothing moves. So we're quite convinced that the bonding was good, but good is good in a lab, but is it good when it's up there? So one thing we can do is we can use some of these paths on the bench which don't actually go to the test masses, and we can see how much did the beam move between the ground and space. And this is a kind of complicated table here, but really what you want to look at is the column called IEBG. That was tested inside the spacecraft in the test campaign, and then flight. And that's the position of the spot on our photodetectors. And the biggest motion we got was about a 14 micron change in one of the signals. You can see some of the other ones about 9 microns. And this is probably not the light moving. This is probably actually the detector moving. Because we only see it, if a beam had wandered up and down, you'd have seen that in every signal. But we actually only see it on one of them. So the glue joint is probably a bit loose, but the rest of it, the actual bench itself, has been pristine. So what did we actually measure? Well, this was a Pathfinder requirement, 9 picometers per root hertz. So that's this funny per root hertz number we use, but just remember the 9 picometers. Over the lifetime of Pathfinder, LISA became a bit more stringent. And it went to 1.4 picometers per root hertz. So we were saying, well, we hopefully we can meet the Pathfinder requirements. If we're lucky, we'll meet the LISA requirements, then we can tick that box off. So we measured the noise again on day number 1. We measured the noise. And we were much better. Now, this is quite a complicated chart to look at because it looks over here as if we don't meet the requirement. But the only thing we're seeing here is the test mass is moving because we can't measure this until we make the test masses free. Then the test masses jiggle around. So the only thing we actually measure is the test mass motion. What we can do is look at the right-hand side where there's no test mass motion because of inertia. So if this line was up here, we'd have met the requirements. If it had been here, we'd have met the LISA requirements, but it's down here. It's down at the order of 30 femtometers per root hertz. So rather than picometers, we're doing femtometers. 1 femtometer is roughly the size of a proton. So it's a phenomenal measurement. So we're 300 times better than requirements. Now, sometimes maybe not Martin, but Thomas Pasfogo used to always shout when he's saying this is over-engineered, you wasted money. And so, well, that was the best measurement we ever made on ground before we launched. And again, it just shows you how quiet space is. This is a measurement you can do in space. You just can't do these kind of measurements on the ground. Even though we thought we could measure the interferometer beforehand, you can't. The ground is just too noisy. And this is to show you that this is our noise budget for the interferometer. And this big line running up here, why we see the noise increasing, the low frequency, this is basically the molecule bouncing off the test masses, which Stefano will come to call the Brownian noise, and that's what limits our performance at the low frequency in terms of the interferometer. So it's not the sensing noise affecting us, it's just the motion of the thing we're measuring. And this has been stable throughout the whole mission. It's not as if it was very good one single day and then it got worse the next day. It's just been constant across the whole time we've been here. All these lines you see jumping up, that's because we've been doing experiments which are deliberately making it worse. So just to finish off, I would like to give, from my side, thanks and congratulations to the whole LISA Pathfinder team. This is not one or two people doing this. And this is quite a nice picture because it shows we have people here coming from the CEST, the project manager, people from the project team, from the flight control team, from industry, science, the PIs, some of the postdocs, and various people. This was really everybody in this picture was responsible for making this mission a success. So it's not one or two people. So thanks to all you guys. I'll finish off with this. This was the start of the science operations. We were quite happy. And the 1st of March at 0800 UTC with a wee bit of champagne. And I will hand over to Stefano, who's going to tell us about the end. So maybe champagne later on, I think, for this one. Thank you. And I should say, this is a life in a PISA. That's what the PISA actually looked like. I can just take this off.
That's okay. No, I haven't. Thank you, Paul. Good evening, everybody. So the original title of this presentation was, thank you. The original title of this presentation was the PI perspective, and then he changed in the program. And if I have just to give you the PI perspective, it's easy. It was a well-done job, and we are really satisfied. If you want a little bit more details, I have to start from where Paul at some point was, that what we have learned from Einstein is that gravity is not an ordinary force. It's not pulling things. It's curving space-time, right? We had to adapt to the idea that even the rays of light, that are very straight things, curve around a massive body. A more mundane manifestation of curvature is the fact that free particles in space next to an heavy body start to curve. Their trajectory are curved, are not anymore straight lines done at constant velocity. What maybe people don't notice very much is that one of the manifestations of the fact that the orbits are curved is that if you look at one particle from the other one, you see the other one accelerating. And actually, the acceleration, the relative acceleration of the two particles is the only manifestation of curvature if you cannot see the source of any other reference. If you take the source out, like in this cartoon, the only thing you see is a particle accelerating, where you go next to a big body that creates curvature. And actually, in this cartoon, I'm also hinting the most practical way to measure this relative acceleration, which is bouncing light out of one of the particles and seeing the color changing because of the Doppler effect. And that's, in essence, how you measure curvature and gravity. And gravitational wave are a wave of curvature, and you detect gravitational wave by looking at acceleration, relative acceleration of distant particles. So a gravitational wave detector is put free particle in motion in space and look if they accelerate. If they accelerate, there is curvature passing by. We are not the only one using this technique to measure curvature. GRACE, the experiment to map the gravitational field of the Earth, used the same technique, 2 test masses and a light beam in between, in which you measure the Doppler shift. This is more or less the speedometer of the police, right? They send an electromagnetic beam on you and collect the beam, the reflected beam. Cassini, the radio science experiment in Cassini, grazing the sun, is the same concept. So LISA is a bit more complicated. You cannot really fly 2 test masses in free space. You have to carry things with you. So you have test masses inside the spacecraft, and you send a light beam from the test mass to the spacecraft to the other spacecraft, and so on, as Paul told you. And in principle, it's very easy to put a test mass in free fall in space, right? You see the astronaut playing with this little ball in the space station. However, if you look carefully at the balls, they continuously move. And sooner or later, they hit the wall, right? So if you want to fly for a long time a test mass free in a spacecraft, you have to do this trick of measuring where the test mass is inside the spacecraft and turn on thruster to have the spacecraft following the test mass. And this is a key element of the LISA scheme, where the test mass is inside the spacecraft, they act as a shield, but the spacecraft has continuously followed the test mass and recenter on the test mass to avoid collision, basically. And to be completely honest with you, The spacecraft follow the test mass in one direction, which is the direction in which you measure, you send the beam, but in all other direction, there is nothing you can do, and you have to push a little bit the test mass with some little force that you generate with electrical field. So you see these test masses here. This is the same as the LISA Pathfinder test mass. It's a cube of gold platinum, 2 kilos. It fits into this box here. It doesn't touch the box, has millimeter on all sides, and is surrounded by little electrodes that are used to apply an electric field and give little force to keep the test mass centered relative to the satellite in all directions except the one on which you measure the gravitational wave. Obviously, LISA is made of 3 of these complement, 2 test masses and a beam, and if you want to see how we thought LISA could look like before the last CDF study, you see that the light from a distant spacecraft is collected by a telescope. The light goes onto this optical bench that Paul was mentioning. This optical bench is the equivalent of the big building of LIGO. All the optics is on an optical bench, and on the back of the optical bench, eventually the light reaches the test mass and make the final measurement. Now the problem is that you would like test mass to accelerate because space-time is curved. But test mass can accelerate for more mundane reasons. In this cartoon, I try to capture gas molecules on steroids, because they aren't so big, hitting the test mass and accelerating the test mass relative to a flat background, and you would see the same thing. If you shoot your police speedometer, you see acceleration, you say, hey, gravitational wave, but it's just molecules, right? And so you have a requirement. Those disturbances must be lower than a certain limit. And now I'll spend a little technical moment on this limit. So this picture is the LISA requirement, and is a spectrum. Spectrum means that this line, if you meet this line at this frequency, you measure a signal. The smallest signal that acceleration signal that LISA can detect is proportional to this line. And being noise, the lower it is, the better off you are, right? The smaller the noise, the more sensitive is your detector, right? So we want to be below that line. LISA must be, the performance of LISA must be below that line, okay? Now, to put the thing in context, frequencies here are very low, right? The lowest frequency I will show you are the inverse of half a day. So we're talking gravitational wave that keeps half a day. You go for lunch, quite full, you do the siesta, you come back, and the wave is coming on the other side, right? Up to waves that last 10 seconds, right? So it's a broad spectrum. And if you want to put the thing in context, this number here, this 10 to the minus 14 meter per second square, as an acceleration, is 1/1000 of a billionth of the acceleration of gravity. If you want to convert in a force, it's the weight of a virus in your hand, right? So it's a very small force. This is one of the scale where each tick is a factor 10, right? So if you go 1 tick up, you're worse by a factor 10 and a factor 100. This cannot be tested on ground. If you try to do free-falling test masses on ground, they free-fall, boom, on the floor, right? That's the end of the experiment. And if you look at what people, as I said, we are not the only one comparing free-falling test masses. If you look what has been done in space, the best thing now is microscope, which is a beautiful French mission testing the equivalence principle. And you may see that, oops, this doesn't work. It's about light. The requirement for microscope, actually, this is not requirement. This is the performance achieved, is 1,000 times less demanding of what we need on LISA. And that was the problem, right? So LISA is a wonderful project, but can it be done, right, at all? Okay. So as Paul was saying, the concept of LISA Pathfinder was simple. Because the disturbances that shake your test mass out of their perfect trajectory are generated locally in the satellite, you can do a test locally. You don't need the 1 million kilometers. So you can take these 2 test masses, put them in a single spacecraft, make the arm length instead of 5 million kilometer, 40 centimeter, put in a single spacecraft, put an interferometer between them to measure the relative acceleration, and you're done. In reality, we have 2 interferometers because we want also to play the trick of measuring the position of the spacecraft relative to the test mass and fire the little rocket to follow the test mass. So we have 2 interferometers. Unfortunately, while in LISA, the two satellites chase their own test masses. Here, the test masses are in the same satellite, so you cannot chase both at the same time. So you chase one, and the other one, I'm sorry to admit, we push a little bit with a little bit of electrical force. And this is a problem. It's a problem because we have to correct in the data, but it's a problem because it's a source of noise. And so we were expecting to be limited by this source of noise. And this is one of the things I will discuss later, talking of performance. So by now you know the story. We took 2 of these test masses, went to L1 because it's quieter. The near Earth orbit, there is too much gravitational gradient, so you cannot use. These 2 gold platinum test mass that you see there is gold platinum because it's very dense. It's a test mass like this is 2 kilo. This very high stability optical bench that carries all the optics, and we needed other things. We needed the electrode housing, the electrode surrounding the test mass to apply the little force. We have to carry ultraviolet light because these test masses are floating in space, irradiated by cosmic ray, they charge up, and there is no wire to ground, right? So we have to illuminate with ultraviolet light and move electrons, steer electrons around to neutralize the test mass. And this infamous caging mechanism, right, to block the test mass at launch, and believe it or not, to handle the vacuum on ground, we also needed everything to be closed in a vacuum enclosure that then we vented to space once in orbit. So this is your only chance to see the real flight hardware, because as you know, tonight we are going to kiss it goodbye. So this is the test mass and paraphernalia, what we call the gravity reference sensor, being assembled at CGS in Milan, actually in Tortona. It's a test mass, but it's also a mirror in an optical system. So all alignment are micron level alignments, right? And this alignment worked very well, as worked marvelously this technique of building an optical structure by gluing the optical component with sodium hydroxide that form again the mirror. So this complicated structure of glass has the same mechanical property as it were machined from the bulk. And this is a jewel done at the University of Glasgow. This is how it looks assembled, and this gives you an impression of the full complement integrated with all the harness and everything in this way to be closed for good inside the space. There are many moments that are for good, right? We saw this this package in 2000. This is 2015. Is the beginning of 2015, and when the guy put a cover on the central cylinder of the satellite, we didn't see this thing again. So you see here being integrated in the satellite. Anyhow, as Paul said, we launched, as everybody has said here, we launched in December. We cruised. We released the test mass so that we have the famous Cesar Garcia dance that is now very popular. To be honest, this is one thing that didn't work by the book. The test mass was supposed to be released and be captured immediately. It bounced a few times. We had to adjust the thing. We had a few moments where, to be honest, I wasn't very happy. But even that we have fixed. Over the last month, Jose and Ian and all the people in the mock have played with this system. And the latest release of the test mass are by the book. What you see here are the 3 coordinates. Sorry, the 3 coordinates of the test mass. You can read the vertical scale is microns, and they are released at some point in some position, and the control system captured them to 0 in a very smooth way with no bouncing. So this worked. The operation were really smooth. The dynamics of the system were really smooth. We have to start this drag-free, where the satellite follow the test mass, and suspend the other one and push a little push little to have the other following. Never done before, all done on paper and simulation. And as soon as we started, what you see here is a plot of the force we have to apply to the test mass to keep it standing. So we started with a big force, and then we go into the drag-free here, and things becomes calmer, and the spacecraft is following the test mass smoothly, and then we transition to this low noise, and you don't see anything. The force that was nanonewton has become femtonewton. You don't see anything, and the system is very quiet. And okay, I think I have to speed up. So what we did, what we achieved. These are the requirements of LISA, right? It's the same plot as before in a different scale. Now, because a single satellite experiment is more noisy, it was expected to be more noisy, the requirement for LISA Pathfinder were very much relaxed. They were relaxed at a factor 10 in amplitude because it was more noisy. And even more, they were relaxed by a large factor in frequency. We were requested only to show performance at a millihertz, 20 minutes. A millihertz is 20 minutes, because testing over the hour is expensive. And so to cut the time of testing, we said, okay, if you demonstrate your performance at a millihertz, we are happy. The only departure from this is that we could have done with a much worse interferometer, but what the hell, we have to do an interferometer for LISA, and so we decided to fly anyhow a picometer per root hertz class interferometer. Okay. What were we expecting? The people say, hey, you over-designed, you got more than. What were we expecting? We had a long error budget. We have done a lot of testing. For over a decade, for instance, we have tested small forces acting on the surface of test masses by making the test masses of LISA Pathfinder the member of what is called a torsion pendulum. So in the horizontal plane, it's a rather sensitive thing. So one of these yellow things is has the same surface as the test mass of LISA Pathfinder, and is surrounded by all the disturbing affair. So we looked if the torsion pendulum was quiet. I'm not going into the details, but we could test all the physical effect we knew would disturb the test masses, and we could even put an upper limit to what we could not predict, which is this line here, which is very close to the LISA Pathfinder requirement. So we flew with a substantial risk reduction that LISA Pathfinder would have completely failed, because we could put, in some ingenious way, upper limit to what we didn't know. And according to our calculation, we should have been dominated by two effects. The first effect comes from the fact that you have to push the test mass, as I said before. Now, you apply a force with an electrical field, but the electrical fields are noisy. And so your force is noisy. And the more the force you have to apply, the more the force is noisy, right? So it depends on how much noise you will get, depends on how much force you have to compensate. And actually, I'm not going into detail, it depends on the setting, on how much force you are prepared to compensate. The second source we thought we would see is Brownian noise, which is, there is gas around the test mass. We pump like hell, but there is still some gas. The gas molecule collide with the test mass, and they shake the test mass and make noise. It's a small molecule, but there are many. And so we were expecting to be dominated by this thing. We calculated how much we expected. You see here the different contribution, but to cut the story short, we thought we should be on the black dashed line. And on March 1st, we were here. So we weren't taken by surprise. We were exactly on the spot, except for the interferometer, which was too good, 100 times good. And so you don't see the razor at high frequency due to the interferometer, because the interferometer is basically irrelevant. You don't see it, right? So, okay, it's Brownian noise and the fact that we are applying this force, and this force is noisy. And are we applying the right force? So how much force we were prepared to apply? Well, why you apply a force at all? The reason is that on board the spacecraft, there is a gravitational field. Most of the gravitational field is this guy here attracting this test mass and vice versa, right? And so we were very brave. what we did, we measured the field created by all the spacecraft. What you see on the left is a log of all the components, where they are, how much they weigh. We calculate the field, and we machine a heavy mass that we put on the other side of the test mass. If you're wrong, you're doomed. Okay? And so we were happy. We thought that the precision of all this calculation was such that we could compensate to a nanonewton. We would be 0 plus or minus a nanonewton. And so we set the system to compensate a nanonewton. But we went up and we measured 25 piconewton. So again, another factor 20 or 30 better. So we could reduce the authority, and going from a force of 650 to a force of 25 or 50, and that's what we got, right? And that's the result we published in June, because we have basically got the LISA requirement with this little trick. You may notice that in the meanwhile, also the Brownian noise, the one due to the molecule collision with the molecule, has gone down. Has gone down because this can is connected through a hose to the outer space, keep pumping, like in the lab. You have the pump pumping, and the pressure goes down and goes down and goes down. So you see the Brownian noise. This is a picture that shows the Brownian noise. This is the most expensive pressure gauge you can think of, right? So this is the pressure around, measured through the Brownian noise going down, as it does when you open a pump on a vacuum can and wait a few months, right? So then, in the meanwhile, the pressure was going down, and so when we started the extension, we were already at a lower level. And the final thing, the final perfect, good, magnificent run we perform is in February, is the red line. And if you average a little bit the data points, that is our spectrum. And you may see that now we are a substantial factor better than the LISA requirement. So, do we understand this? Partly. For the time being, we can account for a third of this noise or half of this noise. We will work for months on the data we already have to understand if we understand everything, but still the performance is such that if we reproduce this system, LISA is done with big margin. We have done other things, but I think I'm running short, so we have published other paper. But more paper are in the pipeline, so this mission will produce many physical review letters. It's an easy prediction. The data are fantastic and are historic. No one has data like this. And if you want to summarize what we have achieved, well, we have now demonstrated that we can do 3 orders of magnitude better than anything that has been done in space in the same field. So I think it's a big leap in space-time metrology. If you want to understand what this means for LISA, this is a simulation. The blue signal is the signal, the acceleration signal between 2 test masses of LISA that you would have if you have 2 black holes of 500,000 solar mass spinning at the edge of the universe, 12 billion here from now. The red line is the noise of LISA Pathfinder, which doesn't look noise at all unless you zoom in. And so you see that this big leap in space-time metrology means that LISA is a precision instrument. It's not like LIGO detecting the thing. It's becoming a deep universe, high-precision instrument for supermassive sources and large sources in the universe. So we also made the front pages of a few things, not as many as LIGO. And the tone of all the front pages is green light for LISA. And indeed, I think this was a green light for LISA because ESA in real time issued the call for L3. And on last month, the SPC, I was in the SPC at the time, selected LISA as the L3 mission. And you know, the schedule, and I'm not going to go into this detail. So if I can summarize a few things, I think this is a bit of an historic mission because we have done many firsts. It's the first space mission in the field of gravitational waves, no doubt. It's the first drag-free gradiometer out of the Earth, you know, at distance from the Earth, and it's certainly the first high-precision gradiometer with an interferometric reading of the displacement. is the first drag-free mission away from the Earth. It's the first ESA mission in the field of gravitation at large. And I think this game of the first can continue for a while. I concur completely, and I want to stress what Paul said. In this instrument, including LISA, there is no separation between instrument and spacecraft. And that has a sociological consequence, that engineers, people from the agency, students, scientists, they have to work together, and we did. And the environment of ESOC was the perfect environment to work together. And the fact that the maneuvering the test masses and the satellite, an essential part of the science operation, makes AOCS and MOC inside the scientific operation of an instrument like this. So I cannot, I concur verbatim with these words by the project manager, Cesar Garcia, who asked me to convey this message. This has been an incredible experience of team working. Not everything was perfect. Working conditions sometimes were harsh, and interpersonal relation tense, as you may see from this picture on the Bodensee with the Friedrichshafen people and other people. The initial team building was really painful. This is a famous gathering in Trento in an 18th century villa, trying to build a team, desperate. The interaction at technical level was also, difficult, as you may see from people from Zurich and Trento and ESA and Friedrichshafen working to make measurement together, and a bit of lack of enthusiasm in the science team also. But this is another aspect. We had to do very sophisticated dynamical simulation of the system with no support from ESA. You may notice that the pen is the laser beam, and the two test masses, you can have them. These are made out of foam, and they proved very useful in the PISA. Yeah, we had to do the data analysis on a stair. I think this gives a good picture of the enthusiastic team of young people and not so young people working to the data analysis in real time of this mission. This is the first mission with the data analysis in real time, maybe. But seriously speaking, the operations were fantastic. And I'm sure I'm talking also for Carsten, saying that we are already missing them, and we will dearly miss it. On a more sad tone, I must say that we were sorry. We had very bad losses during this project. Maybe that's because the project is very long. We have lost Alberto Lobo and Pierre Binetri that were instrumental for the project and for LISA. They carried Spain and France into this endeavor. And we have lost Rudiger Reinhardt, without which fundamental physics in ESA, we would not be here, right? He made a big effort. And so I think I'm sure I'm speaking on behalf of the entire team, dedicating the mission to these three colleagues that we dearly miss. So I think that's the end of my presentation. I think LISA Pathfinder has done his job. It's time to let it go, because I think he has put LISA solidly within the science program, of which we are all proud. And so let's move on with LISA and the science program. Thank you.
Andreas is wondering if I'm going to be able to pull this off here. We'll see with the wireless USB connector. You got it? Ah, there we are. Okay, good afternoon. My name is Phil Barella, and I'm the project manager for the NASA JPL contribution to the LISA Pathfinder mission. Sorry, I walk, so. First order of business is just a heartfelt congratulations to ESA on a miraculous, wonderfully executed mission. And we're from NASA and JPL, congratulations. You guys have done a wonderful job. The execution and operations was phenomenal. I've been on several projects, and you guys just carried out a wonderful mission, and we were so happy to be a part of it. I do have to tell you, if you look at any large endeavor, there's typically a team. behind that large endeavor. Very seldom do you see one person or even a handful. And we had a great team, not only at JPL and at NASA, but over here with the ESA team, including the ESA prime contractor Astronomy. I see Dave Welty in the group there. And to give you a sense, I mean, I loved going through the history with that Paul presented and Stefano. We started at JPL, the project, the NASA JPL project, in late 2002, early 2003. I came on board in 2005, and so it's been a long journey for us. And as you can imagine, similar to NISA's technology development, this is a technology demonstration. So for NASA and JPL, what this means is that we hoped to learn, not only in operations, but during development, we hope to learn the challenges of this technology. I mean, taking concepts off a whiteboard, building prototypes, qualifying it for space, and actually operating it. And as you can imagine, we ran into a number of bumps in the road along the way during development. I remember Jacques Louet in 2006 at our CDR. For those of you that remember Jacques Louet, he's retired now. He sternly warned me. The first time I met him, I went to shake his hand, and he didn't shake my hand, but he sternly pointed his finger at me. He said, "You better deliver on time, or I'm going to throw you off the spacecraft." I was happy he retired the following year and didn't see our 1 year delay in our delivery. But there were a number of bumps in the roads that our technical team overcame. There were a number of bumps in the roads during operations that we overcame as well. And without Andreas and Damian and Ian and the STech team, Paul McNamara, just world-class team, really helped us, and we couldn't have done it without you. So, and that's an understatement. And for those of you who know what was going on in operations and the workarounds that we had to enact to make it successful, it really is an understatement. So the collaboration was just phenomenal. And one of the messages I deliver back at NASA when I get a chance to present about ST7 is just that. We had a wonderful team, and you guys were great and very supportive when we needed you most. So thank you. Okay, I'm going to present a few charts, and I'm going to hand it over to Colleen Maurice Redding, who is in the back of the room there. And Colleen is our propulsion technologist. She led our extended mission, taking over for John Zemer. Many of you know John Zemer. And she'll give you some of the details of the operations. Hopefully I didn't leave anybody out, but just a great team here. Okay, so I'm not going to belabor the teaming, but as you can see, that's a central theme here for us. We're so happy and honored to have been able to participate in the LISA Pathfinder mission. We're ecstatic not only with your success, we're ecstatic with what we learned and having the opportunity to work on this technology and take this concept off the whiteboard, actually qualify it for space, and then operate it. Tremendous success for NASA and JPL. Back home, we have BUSIC, which was responsible for our thruster development with JPL technical support. We flew a RAD 750. Many missions at JPL have a RAD 750 dedicated to the entire spacecraft. And so that's the kind of processing horsepower we had. To be fair, we didn't need it all initially, but because of the workaround that we had to enact during operations, we're very happy we had it. It saved the day having that RAD 750 for the ST7. Goddard Space Flight Systems, another excellent partner, was responsible for the algorithm development, the dynamic control system, and then, of course, JPL doing flight software, the thruster development with BUSIC, structures, cabling, and what have you. We went through our delivery review in June of 2008. We installed on the spacecraft, I think, September, October 2009 timeframe. And then the team, as teams do, went off and did other things for a while. And so one of the main challenges that we had was keeping the core competency together at JPL and NASA. As you can imagine, going into operations with a very complex instrument payload like this, not just that you can't just call somebody, a month before operations and ask them to step in. And fortunately, we were. Many of us have gone and worked I've worked 3 other projects since I went through our delivery review in 2008. But we were able to keep that continuity and the core people. We had some new people come in, but the core people were part of the team. I got to mention again Airbus. Dave Welty back there has just been a wonderful partner and part of the team. And of course ESA. And when I say ESA, I mean STech, ESOC, ESAC. Hopefully I'm not forgetting anybody, but all through the development, just a great team. Now I mentioned we started in 2003 as a project at JPL in earnest. So you can imagine that's 14 years. It's kind of like growing up with a sibling, right? A brother or sister. You're going to fight. There's going to be disagreements. There's going to be some conflict. And so we tried, before launch, actually, we tried to resolve conflict in a more amicable way than sending emails and being mad at each other. And so this is at my house. And you see Paul McNamara here playing pool, and the project science support at JPL, Kurt Cutler. And we thought it'd be a fun idea, because we wanted more operating time than what we had. And we thought it'd be a fun game to challenge the project scientists at some pool, and also the project manager, Caesar, as well, and say, hey, if we win, we get some more operating time. So let me just give you some advice. If Paul ever challenges you to play pool in anything, don't do it. He is a phenomenal pool player, and I'm not quite sure where he gained, I guess, all the years in grad school in the pool hall, but he won. Nonetheless, ESA was still very generous with the operating time and actually gave us more. When I prepared these charts, I wasn't quite sure who was going to be here in the audience, but I thought it was fair to talk about micronewton level thrust and what that means in simple terms. Even at JPL, when we're in a room full of engineers and you start talking about position control and thruster noise in nanometer per root hertz increments, the eyes start to roll in the back of the head. And when you start to, even 30 micronewtons, when you talk about our maximum thrust of 30 micronewtons or our minimum thrust of 5.5 micronewtons, yeah, you understand the units, but just understanding what that really means and 0.1 micronewton control authority. So we put together some simple cartoons that we've used over the years. 30 micronewtons in a 1G environment, which is the maximum design thrust that we designed our thrusters for, is effectively equivalent to lifting a 3 milligram grain of sand. Or put another way, equal to the mass of your average mosquito. I'm not sure if that's before feeding or after, but now that's great. That's the maximum thrust. And in fact, during operations, we actually saw 60 micronewtons on several of our thrusters. We did a test that was fairly risky. We didn't want to do it till the extended mission, and we doubled that. So we were very happy about that. But the real claim to fame of this propulsion system that we delivered is the control authority in 0.1 micronewtons. So from about 5.5 micronewtons up to 30 micronewtons, our control authority is in 0.1 micronewtons. And so that's about the mass of the antenna on that same mosquito. And so I think it helps most people understand we're talking about a very precise propulsion system. And as Paul and Stefano told you, what LISA Pathfinder attempted to do and what LISA needs to do in keeping that spacecraft still, you have to have that kind of control. And so we're elated. We demonstrated it and showed that we could meet all of our level ones, and Colleen will talk to you more about that in just a moment. I'm not going to belabor this photo, but I just wanted to describe you'll see this photo here and this photo, or this cartoon, is meant to be one of our cluster heads. We have, what you see mounted on the spacecraft there is what we call a cluster, a thruster cluster, and that's 4 thruster heads. There's one mounted on the opposing side of the LISA Pathfinder spacecraft as well. Each one of those clusters, you can see there, has 4 thruster heads. Each thruster has 9 emitters, so we have a total of 72 emitters. And the avionics RAD 750 I described earlier is mounted inside. And I think that's all I'm going to say about that chart there. So I won't spend a lot of time on this. I just wanted to, I highlighted earlier the bumps in the road that we hit and the innovative excellence really back with our team, our entire team. It was a tough road. And to get this propulsion system from what was a concept, we started a research activity back in 2001. Colleen and her group were part of that. To take it to flight qualification level and then to operations level, it was truly a technology development, one of the hardest things I've ever delivered in my career. So it was a really, truly excellent technology development program by the folks back at ESOC and JPL and the whole team. The good news, we met all of our level ones. So level ones in the NASA vernacular are how they grade a project. So before launch, your level ones are established, and NASA says you're successful, 100% successful as a project if you meet the following requirements. We met all of our requirements. And so for the project, that's just excellent, and again, we're ecstatic. And at this point, I'm going to turn it over to Colleen, and she's going to describe a little bit more about the level ones and the other operations. Thank you.
Okay, so this slide, the data in this slide shows that we met the level 1 requirement of position stability. So is this, the data in blue here shows that we delivered the requirement, which was 10 nanometers per root hertz and this is the requirement shown in red, and we demonstrated that with margin. So that was the most important requirement that we had to meet. The second one was the thrust noise. So the data here shows that we met the thrust noise requirement. So it's shown here in red, a 0.1 micronewton per root hertz. And we met that with margin, more margin in some frequencies. We did this in an accelerometer mode, so that's using the test masses as accelerometers to measure the thrust. We did this, the experiment was run with 23 millihertz signal injections to the thruster. So this is an artifact of the test and the way we ran it. It's not actually the thrust noise. So that shows we met the second most significant level 1 requirement. So to add to the first for this mission, we demonstrated electrospray thrusters, the colloid thrusters, for the first time. It's incredibly exciting to us because we had been working on them for quite a while. They've been under development all around the world for tens of years. So this was incredibly exciting that we finally had a mission that actually required this technology, and we're able to demonstrate it. We met our propulsion requirements in flight. The objective for the thrust range for the thrusters was 5 to 30 micronewtons. We demonstrated 5 to 30 micronewtons on all the thrusters and up to 50 on one thruster and 60 micronewtons on another thruster. The precision requirement was 0.1 micronewton, and we demonstrated that also in flight. Thrust noise requirement, 0.1 micronewtons per root hertz. We demonstrated that in flight on 7 thrusters. One of the thrusters, thruster 1, had one needle that was flickering off and on. So that created a higher noise level. That was about 0.8 micronewtons per root hertz. So the thrust range response time, so that's the time to go from 5 micronewtons to 30 micronewtons. The requirement on that was 100 seconds. On the ground test, we demonstrated that within 10 seconds on all 8 thrusters. In flight, we demonstrated on 7 thrusters. In thruster 8, also had a slower response time of about 146 seconds. The operational lifetime, there was a point it was 90 days, then it was reduced to 60 days because it was delivered and then was sitting on the spacecraft for 7 years. That requirement was also relaxed. So it was just that the requirement for lifetime was any measurable thrust on orbit. So there were tests done on the ground for 3,478 hours. All thrusters, 7 of the thrusters demonstrate over 2,400 hours in space, which is 100 days, and one thruster, thruster 4, that was mentioned earlier that shorted out, demonstrated 1,690 hours, which is about 70 days. So this is exciting for us because this is the demonstration of a new propulsion technology, electrospray thrusters. There were some issues that were mentioned, but we think we know how to address them and develop the technology further for missions like LISA or for precision pointing for exoplanet observatories is another application for it. So this is a summary of our experiments in the primary mission, which was about 90 days. We conducted about 14 experiments, so this is to show you that we used our time wisely. We're so grateful for all the support we had from everybody, especially Ian and Jose. By the end of the primary mission, we joked that Jose knew how to run our thrusters as well as we did. And so he was helping us out to develop the experiments and run them. We had about 15 experiments in the extended mission. All of our experiments fit into 3 three categories: drag-free control, demonstration, performance, and then improvements and optimization, thruster performance, demonstration, characterization and improvements, and thruster performance model validation. So C1 was our first experiment that demonstrated our level 1 requirements of the thrust noise, precision, position noise. It also demonstrated all of our modes. We had 6 modes: standby, attitude, 0G, accelerometer, drag-free, 18 DOF, transitional, and 18 DOF. So those were all demonstrated with that one experiment. We did many other experiments. C2 was basically measuring the test mass actuation response. So that was important in calibrating the position measurement. We had some issues with those measurements. They weren't precise enough in a not in a high-resolution mode. So we're very grateful that we got to run the extended mission because we were able to run those calibrations, rerun the calibrations in a wider range, in a higher resolution mode, because we needed to calibrate the inertial sensor on all axes. So we're able to do that. We needed a flight software modification for that. But that enabled us then to do measurements where we would inject signals in the thrusters, and we could actually measure the thrust using the test masses as accelerometers. We could measure the thrust levels of all the thrusters, and that enabled us then to validate our thruster performance model, which I'll show you is very simple. We did many other experiments. We did experiments to run on only 7 thrusters, which turned out to be important in the extended mission because we needed to run with only 7 thrusters. As mentioned, we had four cold gas thrusters were running in a crutch mode to help support us. DFACs actually ran also with our colloid thrusters instead of the cold gas thrusters, and they were able to demonstrate better performance. And then we did cathode tests, and we also did several tests where we improved the thruster control algorithm to improve response times to actually reduce the thruster noise. And then experiment that was already mentioned was that we, the primary mission requirements were that we run from 5 to 30 micronewtons, and we were able to demonstrate that we could run up to 60 micronewtons with one of the thrusters to demonstrate extended range capability in case that was necessary. So the summary of what was accomplished in our mission, ST7 was a successful demonstration of a drag-free control at a performance level necessary for a LISA-type gravitational wave observatory. We showed that the space disturbance environment is understood at the 0.1 micronewton per hertz level. The DRS met all the level 1 position and thrust noise requirements. The European LTP inertial sensor functioned in the DRS system as expected. The 18 degree of freedom drag-free control operated reliably in our system. The self-gravity model of DRS is correct at the few picometer per second squared level. The colloid thrusters and the thrust model were both validated in flight, and that's how simple our thrust model is. But in measuring thrust, we were able to determine what the C1 coefficient is. And that basically is depends on the propellant properties and temperatures. Carbon nanotubes also were demonstrated in flight, and the colloid thrusters demonstrated an extended range of 60 micronewtons. And so thank you so much for your support. It was an exciting mission for us, and we are so grateful for being a part of your mission. Thank you. Congratulations.
I did. It's red. LISA Pathfinder may be gone soon. But we shouldn't really feel sorry, because now is the time for LISA to go, and we're ready. I have good news for you, because on June 20th, ESA's SPC has selected ESA L3 as the LISA mission. This is very timely. It's only 21 years after the first LISA symposium, and here we see a picture that we've already seen once. You may recognize a few of these faces. Of course, they're much more beautiful now a few years later. LISA is really a mature concept by now because it goes back long before the first LISA symposium. It was actually conceived in 1992 in the Chilean Andes, when after the GRG meeting, a bunch of us got stuck there because the baggage handlers were on strike and we couldn't get away. And what do scientists do? When they are stuck in the mountains, they invent a new mission. That was the birth of LISA as we knew it. In those days, it had 4 spacecraft. Soon after, it became a cornerstone, and then the 3 spacecraft version of it appeared in 1997. The basic principle of that has been unchanged ever since in the following 20 years. It went through a lot of studies, actually through 6 years of joint mission formulation studies from 2005 to 2011, then with a little dark ages in between, now known as the ELISA or Evolving LISA times. Now we're back to where we were, and we have 3 arms again in the mission, as is proper for LISA. Let me remind you, there was in March 2011 when Europe decided they had to make do without NASA. Those were not so good days for us, because it meant we basically had to redesign a mission for half the money and prove we could do the same science. This little exercise is known as de-scoping, and of course we did that, like all the other big mission proposers in those days. And what do you do? First, the usual things: make the arms shorter, make the telescope smaller, save on mass, use simpler orbits, use a cheaper launcher, which was a Russian steam engine. But you also have to show pain, so people believe that you can actually save half the money on this. How do you show pain? Well, it's easy. You cut off an arm. And that's what we did. De-scoping is an art. We really learned it, and that's what came out of this. In bureaucrats' language known as NGO. And as you see, it only has 2 arms. But if you look closely, you see it has 60 degrees between the arms. And also the 3 spacecraft look almost identical, except that the 2 daughter spacecraft there are lacking a telescope. It's kind of obvious what you could do. Easily, you could insert 2 telescopes and you're back to the old LISA. And that was the hope all the time, that through international contributions we could get there. But for a while, it didn't look good. But then came 2015 and 2016. And 2 things happened in those years. The first thing was this: the cover of Physical Review Letters, the first discovery of gravitational waves here on the ground. And now the discovery of black holes with gravitational waves is almost commonplace. Almost as many black holes have now been discovered with gravitational waves as with X-rays before, and pretty soon we will take over. It's also easy, because if you look at this, then with every discovery with gravitational waves, you get 3 black holes, and not just 1, right? The 2 you start with, and the 3rd one that comes out of it. So now we have 12, and, well, watch the press. And the second thing that happened was LISA Pathfinder, testing LISA technology. And again, we made the cover of Physical Review Letters. And what did we do? We had created the stillest place in the universe. And Stefano has already told us it is more sensitive than the weight of a virus that is sitting down on one of the proof masses with a big chunk. ESA has reacted, and actually the call for mission concepts came out much earlier than was anticipated, 3 to 4 years earlier, already in fall of 2016. And the best thing is, even NASA is back now. NASA is back in LISA, not the least because of this glowing report here, the midterm assessment of the decadal review, fittingly called New Worlds, New Horizons. NASA always has these wonderful titles for their reports. I love these. The call came out. We answered with our proposal on January 13th. If you haven't downloaded it yet, you can download this wonderful booklet. It only has 42 pages. And as you know, 42 is the answer to everything. It's easy reading, and it's probably the best publication on low-frequency gravitational wave astronomy ever written. So we put a lot of effort into it, so please read it. And then it happened. On 20th of June, it was selected as L3. What did we go into the selection with? With well-thought-out requirements. And I will not explain how we arrived at the envelope of all of these requirements. You can read it up in the book where any of these colors has a well-defined meaning in there. The good thing is that these requirements set an envelope of the sensitivity curve. Those are the borderline cases that determine our science case. But the good thing is most of the science is in the empty part in the middle. And that means the non-borderline cases, our bread and butter science, is very high precision spectroscopy of mainly supermassive black holes, but also of many, many other objects in the world. And this sensitivity curve was just a requirement. And now we've seen that was the requirement, and that's where we are. So we have the full sensitivity already demonstrated on LISA Pathfinder. All we got to do for LISA is build it again, but with longer arms this time, quite a bit longer, I admit. Go from 38 centimeters to 2.5 million, and then you get all this science out, which I'm not going to talk about. I just wanted to show it to impress you a little bit. I only want to talk about one thing on there, and that is black hole astronomy. This here is the parameter space of black holes as it will be known by 2030. And plotted there is the distance in terms of redshift. So at the bottom is 0 here and now in this lab. In the middle is 10, roughly, reionization. And then above are the dark ages. The farthest known objects ever observed so far at redshifts of 6, 7, 8 in this diagram. On the horizontal axis, you see the mass of the black hole as a logarithm. There's 1,000, 1,000,000, and 1,000,000,000. And now by 2030, we will have marvelous new telescopes like the LSST, the large telescopes, very large telescopes, extremely large telescopes, and overwhelmingly large telescopes. And even the James Webb Space Telescope will probably have left the ground by then. And these marvelous new telescopes will cover the high end of the mass scale of black holes out to about reionization. At the low end of the mass scale, you see the gravitational wave detectors, which are already in operation. Advanced LIGO, advanced Virgo, and soon CAGRA. And you see the gravitational wave detectors proper, they cover the low end of the mass range out to redshifts of maybe 2. Now, if the third generation gravitational wave detectors like ET or Cosmic Explorer are working, they will go to slightly higher masses and out to about reionization. But you see easily the whole middle range of the parameter space will still be uncovered by 2030. And now it is your guess. Where in this diagram do you think LISA will be sensitive? Yes, right there. Smack in the middle, with superb high signal-to-noise ratio, it will observe black holes out to almost arbitrary redshift if they do exist, which, of course, we don't know yet, but it'll fly soon. We've seen this diagram already, and let me point out that this is a weak signal. This is only a 100,000 solar mass black hole binary, and it's at a redshift of 5. Which is almost at the edge of the known universe as we know it right now. It's a weak signal for LISA. And what's plotted here underneath in red is the real experimental noise as we have measured it on Pathfinder. We don't need to extrapolate and guess anymore. We have measured it. And you see what I mean by high signal-to-noise ratio observations. You have a very hard time even seeing the noise on this diagram. So this will be high-precision spectroscopy. And even better, the black holes that LIGO is seeing, had LISA been operating 10 years ago, we would have seen them 10 years ago, because now they were entering the LIGO observational sensitivity window at 30 hertz and exiting at 250 hertz. That's because right now they're very close. But 10 years ago, they were far apart and were slowly circling each other with 10 millihertz frequencies. And if you follow the black curve backwards in time, then you see that 10 years ago, these LIGO black holes were smack in the middle of the LISA sensitivity curve. Not only would we have detected them 10 years ago, but we could have predicted the time of merger to a second and the space in the sky where it would happen to a fraction of a square degree. And I can guarantee you that any big piece of glass on this planet would have looked in that direction during that second, trying to find a glimpse of this electromagnetic radiation. So, we are proceeding. The call for mission concepts is out. LISA is selected. Decision on the L3 adoption will come in the early 20s. L2 in 28, L3 in 34. We, of course, shall be ready for an early launch. And I've taken the liberty of quoting here from the purely technology-driven schedule by the Gravitational Observatory Advisory Team to ESA. And if you can't see what it says there, where the line for launch date is, then I highlight it for you. It's in 2029, as given only by technological readiness. So all that's required is 1 billion. Come on. And we better hurry up, because I will have a long life, and I want to hear the Big Bang, and I will, in gravitational waves, and you also will do that. Thank you.
So, thank you very much for so many excellent presentations. I have to say, it was really amazing. Having said that, of course, there's now the chance for question and answers to the audience. So if there's any questions that you may want to ask to our presenters, it's your opportunity. Questions? No questions? Still digesting. Okay. You gave all the answers in the presentations. They were so. What can you ask? Okay. So I think thank you very much to all the presenters. Thank you very much to you for being here with us. And I think in around about 2 hours we will be exercising the last command from the main control room. So thanks.